Okay, so let's solve the following application. An electrical circuit with a resistance of 100 ohms, a capacitance of 0.01 farads, and a constant forcing of 100 volts. Find the current I of t in amperes if the capacitor is initially uncharged. Okay, so to write out our ODE, let's go ahead and start at some point A on our circuit. And this is the high side, and this is the low side of our potential. And as we proceed around, we'll have two loss mechanisms, one at the capacitor and one at the resistor. And so we'll see them as loss mechanisms. So we'll use minus signs as we proceed. And as I go across the source, I pick up energy to the tune of E of t, and the potential drop across the capacitor is 1 over C times the charge, which is a function of time. And as we proceed around to the resistor, we call Ohm's law, which is a minus R times I of t. And Kirchhoff's second law says that by the time we make it back to A, the net potential should be 0 around any one loop. So as we proceed around, there should be no gain or loss in potential. Okay, so if I rearrange this equation, let's see, I write this as R I of t plus 1 over C Q of t is equal to E of t. And here again we have to recall that by definition current is defined as the rate of change or the movement of charge carriers. Without any movement, of course, like in static charge, there's no such thing as current. Well, there is no current. Okay, so let's go ahead and change the I to dq dt. I'll just write this as q dot of t, and I'll probably drop the of t, or the function of dependence on time. So I write this as r q dot plus 1 over c q is equal to E of t. And so now we have an ODE in just charge, and it's first order. So let's go ahead and divide out by the r on the leading term. And I write this as q dot plus 1 over rc q is equal to, I'll just write as E over R, again dropping that time dependence. Okay, so I guess I'll solve in general and then I'll plug in some numbers later because it doesn't matter. I'm just going to carry around the R, or the C, and the E. So if I want to solve this next, I'm ready for an integrating factor. And my integrating factor in this case is going to be E to the integral of, and this would be like my P of X, be 1 over RC with respect to time, which is the independent variable. So here I get E to the T over RC. And of course, if I multiply by both sides, I know on the left-hand side I'll get an exact differential, in which case I'll have, let's say, d by dt of the function q of t times the integrating factor, e to the t over rc. On the right hand side, I'll just have e over r times e to the t over rc. So at this point I'm ready to integrate with respect to time, and on the left hand side I'll just get qe to the t over rc from the first fundamental theorem of calculus, and then here I'll get e over r times the integral of e to the t over rc dt. And if we recall, the integral of e to the alpha t is 1 over alpha, but in this case alpha is 1 over rc, so I'll get 1 over 1 over rc, which just becomes e over r times the rc times e to the t over rc. And of course I have to add some arbitrary constant. And I'm going to call it C1 so that I don't confuse it with the capacitance. These electrical problems can be, I guess, a little difficult in that the C can stand for capacitance. You have to be careful with your constant. It can also represent the measure of charge, which is a coulomb. So you'll see a lot of capital C's in solving an RC circuit. Okay, and notice that I could have distributed the E over R to the constant term, but again, it just becomes another constant anyway, and I won't really determine it until I apply some initial condition. So if I write this out, I'll get QE to the T over RC is equal to, and I have E over R times RC, so this gives me EC times E to the T over RC plus C1. Okay, so let's divide both sides by E to the T over RC, or you can say that you're multiplying both sides by E to the minus T over RC. And on the left hand side, you just end up with the function Q of T is equal to, well, here I have an EC, and then plus C1 E to the minus T over RC. I could let RC equal tau. I mean, it's just a time constant. For the circuit, EC I can recognize as just another charge, of course. Remember the potential drop on the capacitor was 1 over CQ. So if we say E is 1 over CQ, then EC is going to be some charge Q, or the maximum charge on that this capacitor can take given that potential and this capacitance. So I could write this as like some capital Q, but I'll just leave it as it is. Okay, so now we need to apply some initial condition, and I'm going to get that from the fact that the capacitor is initially uncharged. So what that's really saying is that I have some Q at time t equals 0 is equal to 0 coulombs. Okay, so it's initially uncharged. There is no charge at time t is equal to 0. So I'll get 0, put that over here. So I get 0 equals, for Q, EC plus C1, because e to the 0 will just be 1. It says that C1 is going to be a minus EC. So I get Q of T is equal to EC minus EC E to the minus T over RC R. Q of T is equal to, if I factor out an EC, 1 minus E to the minus T over RC. And again, I could write this EC as some Q max, or just some Q or Q naught or some other Q, and write it as just Q of T is equal to Q, capital Q, say 1 minus E to the minus T over RC. But for now, I'll just leave it like this, and then maybe we'll plug in some numbers and see what this thing does. So I have E times C, that's going to be 100 times 0.01, well, that's just going to be 1. Then I have 1 minus E to the minus T over RC. So R is 100 and C is 0.01, so 100 times 0.01 is also 1. So this actually becomes fairly simple. And let's see, I get Q of T is equal to 1 times 1 minus E to the minus T. So I really just get 1 minus E to the minus T. And I wanted to find the current, so recall that the current is the rate of change in charge, so I get I of T is equal to, and if I take the derivatives, I just get E to the minus T. Okay, and that sort of makes sense. So let me just go to the next page, and let's see what we have here. Okay, so I have Q of T is 1 minus, okay, so if I write this out, I'll get, let's see, Q of T is equal to 1 minus E to the minus T, and we said that I of T was just E to the minus T. And if we look at the plots over to the right, it should be clear that if I do a steady state analysis, I'll take the limit as time t goes to infinity on Q of T. I'll just call it, say, QSS, Q steady state. It's going to be, I get 1 minus, Well, e to the minus t, as time gets very, very large, becomes 1 over e to the infinity, which drives to 0. So this thing approaches 1. And if I take the limit as time goes to infinity on I of t, I can call this ISS, this thing clearly approaches 0. So, and that makes sense. So if we look at this, and if we go back to the time constant, RC, so the time constant we said was at 1 second, so this is about 1 second on the graph, on both graphs. And so at 1 second, the charge should have risen to about 63.2% of its max value. And it's kind of tough to really say when you're going to be at a 100% value because of the exponential. It's going to asymptotically, of course, approach 1. And so that's why we use this time constant. And the same thing's true for the current. The current will have fallen off 63.2% after one time constant.